Hi all, welcome to our first condensed matter seminar at the Burlington campus. This is our first quantum material and sensing institute condensed matter seminar. Today we have the pleasure of having
Okay. Thanks to Alberto for the introduction and invitation. So today I'll talk about Terahertz nonlinear magnonics. Is the audio okay? Yeah. Okay. Yeah. Cool.
And the audience, they can hear us.
Okay, so I'll explain what Terahertz nonlinear magnonics means as it goes. But first, I want to share with you this picture of how ocean waves interact with each other. So in this picture, you can see that there are two shallow ocean waves that meet with each other and flag into to form another ocean wave whose height is much taller than the height of the previous two. So this author wrote a paper to describe this phenomenon and explain that such a phenomenon can only be explained by taking account into the nonlinear interaction between the ocean waves. And the second thing they point out is that it was thought that such nonlinear interactions are rare events, but they are not. That's essentially the two important pieces of information that I want to give you today. That is, first, nonlinearity is essential to explain many exotic phenomena that we have seen. And the second is that the nonlinearity may not be that uncommon as we used to think. Okay, but instead of just illustrating this idea using ocean waves, I want to tell you that that is also true in driven quantum materials as a playground. So when we think about condensed matter system, we usually think about the collective excitations of charge, phonon, or spin degrees of freedom. And when we do measurements, what we usually do is just to perturb the system around the free energy surface, and then we get a response in the linear response regime. But if we have a strong tailored laser light that can resonantly excite these collective motions, we are able to drive them strongly to the nonlinear regime. And that's where all this unharmonicity and the surprise comes to you. Okay, so in this talk, I'll focus on the spin excitation, or more broadly, the collective excitation of spin waves or magnon modes. And this collective excitation are thought to be play an important role in the next generation signal processing techniques, such as this magnon to current converter, and for this fast signal processing using spintronics. But fundamentally, the control of spin waves is difficult because meaning the light is weakly coupled to these collective excitations. Here I'm showing a pioneering work by Professor Tobias Humphreys. In this experiment, they use an intense Terahertz pulse to drive the antiferromagnet, and they observe these long-lived oscillations probed by the Faraday rotation. Okay, this is very nice, but if you, yeah.
Experimentalist, so I'd like to know the bottom part of the thing, and you made a little gap there. All of a sudden, the frequency changes. What does that mean, children?
Yeah, it's basically like when you drive the system, so this spin starts to oscillate, and then they are manifested in a time domain as a signal of how the magnetization changes. So this is a time domain picture of how spin waves are excited and oscillate in time.
That part. Okay, it is correct. You plotted the wave in two different scale. You use two different scale, right? So that's the frequency is more or less the same.
Yeah.
Okay.
Yeah. Okay.
Oh, sure.
So if they do a field dependence measurement, so to plot the magnetization amplitude as a function of how the terahertz field strength changes, you see that it scales linearly. So that means it never goes to the nonlinear regime. That's because the fundamental interaction between the terahertz pulse and the spin excitation is from this linear Zeeman interaction. So this terahertz, yeah.
Pump and air probe.
This is terahertz pump and near IR probe through the Faraday rotation. So this terahertz magnetic control of spin waves has been known for quite some time, but it largely remains in the linear excitation region. So what we want to do is to push this excitation region into the nonlinear response region. So with that said, there are examples of driving magnon modes to the nonlinear regime. For example, if you take a very strong microwave photon to pump the ferromagnets or ferromagnets beyond threshold, you can do bifurcation to generate two magnon modes with opposite momentum to conserve the energy. So this is essentially a nonlinear photon-magnon interaction. If you go to higher frequency, for example, to the mid-infrared, one can use a laser pulse to be resonant with lattice vibrations. And this is an example that people drive the chiral phonons, which couple to the magnon modes. So this is another channel to non-linearly drive a magnon mode. But if you go to the frequency in between, this is where the fundamental energy of the spin excitation is a terahertz excitation. So we can think about whether we can drive the magnon through their nonlinear magnon-magnon interactions. So that's basically what I want to tell you today. I want to talk about 3 stories about this terahertz nonlinear magnonics by taking the advantage of the nonlinear magnon-magnon interactions. Okay. So we will focus on this class of system called real Earth ultrafast. From the textbook, we are educated that there are generally 2 types of magnets. One is a ferromagnet in which all the spins are parallel to each other, and the other is antiferromagnets in which the adjacent spins are anti-parallel to each other. So in these compounds, in the magnetic unit cell, the 2 sublattice spins are anti-parallelly aligned, but they are also slightly canted to give rise to a magnetization. As such, there are 2 fundamental magnon modes in the system. One is this quasi-ferromagnetic mode, which manifests as a precession of the magnetization. And the other is this quasi-antiferromagnetic mode, which shows as the amplitude oscillation of the magnetization. And these modes also follow specific selection rules. So if we have a terahertz magnetic field, which is perpendicular to the magnetization, we only excite this quasi-ferromagnetic mode. However, if the terahertz magnetic field is parallel to the magnetization, we instead drive this quasi-antiferromagnetic magnon mode. Okay. So first, we can do some simple experiments to show that this symmetry is valid. So if we take a terahertz pulse whose magnetic field is parallel to the A-axis, that means the terahertz magnetic field is perpendicular to the magnetization. You can see this very slow oscillation in the time domain whose Fourier transform correspond to this low frequency magnon mode, which is. If we now rotate the terahertz magnetic field by 90 degrees, we instead drive this fast oscillation mode, which is the QF mode as shown in here. If we align the terahertz magnetic field in between, for example, at 45 degrees between the 2 axes, we see that we can drive both magnon modes. So by doing this type of measurement, we can selectively control whether we drive either magnon mode or both. So to make more sophisticated measurement to show the symmetry, we can put the sample on rotating stage and rotate it every 5 degrees and measure the terahertz linear response. And we can do a linear polarimetry pattern. As you can see here, the QFM mode can only be driven when there's a magnetic component projecting onto the A-axis, while for the QAF mode, it can only be driven when there is a Terahertz magnetic field along the C-axis. So this measurement shows the linear response of the magnon modes, and they really looks like they are two distinct magnon modes. So the question is that, can we probe the nonlinear couplings between these magnon modes, and are they intrinsically coupled? And that's actually not an easy experiment to do, because fundamentally, the magnon modes are weakly coupled with light. So usually, as I said, when you drive the system, you always see the linear response. And second, if you just take this 1D spectroscopy and measure the response as it occurs, for example, if you drive the two modes, you see two peaks, but you don't know whether these two peaks are coupled. So solution is to extend the 1D spectroscopy to this 2D map so that you can correlate the excitation energy and the detection energy. In this case, for example, the peaks along the diagonal line are from the nonlinear excitations of the single mode alone. However, if you get a cross peak whose excitation frequency and the detection frequency are different, that means you drive one mode but detect the other mode. Yeah, go ahead.
I mean, this is a broadband pulse or like a...
It's a broadband pulse.
Oh.
Yeah, but we do some tricks so that we can do this frequency correlation now. I'll tell you very soon. Okay, so this is the spectroscopy information that we want, but how can we do it? So we do it by take like a sequence of strong field Fourier pulse, which are broadband in nature. And then we vary the delay between these two pulses and also measure the signal emission as a function of signal detection time. So there are intrinsically two detection times that we need to vary. One is this interpulse delay, and the other is the detection time. And then we run a 2D Fourier transform to generate this 2D spectrum. Okay. So in a simple case of a single pulse experiment, it's done by driving the system with a single pulse, and then you look at the signal emission afterwards. This is analogous to this sequence of imaging I attached here. So if you drop one water droplet into the water pool, you can use this high-speed photography technique developed by the MIT professor Edgerton, so that you can visualize the dynamics of how a water droplet hitting the pool of water. Okay, but you can imagine that now you can drop two water droplets and then they also interact with each other. So in this case, by doing so, you can get these funny patterns like a cone or umbrella or mushroom, depending on the time separation between the two water droplets. So in this case, not only the dynamics matters, but also the timing between how you, when you drop the water droplets also matters. So in this case, this is analogous to the double pulse experiment that we are doing. So we have two time delays. One is the interpulse delay, and the other is the signal detection time. So if we vary these two delays, we can generate this 2D time plot, which basically is a time correlation function of a nonlinear signal. We extract the nonlinear signal by taking the first signal that subtract both the signal of the first pulse alone and the signal of the second pulse alone. So this is a residual of the nonlinear signal with a part that means 1 + 1 is greater than 2. But as you may be aware that this technique is intrinsically very time-consuming because you need to vary two time delays. So typical data acquisition times around a few days per spectrum, which is too long for systematic studies. That is because to detect the Terahertz photon is actually very challenging. The conventional way of how people detect the Terahertz signal is to focus the Terahertz signal onto this electro-optical sampling crystal. And then you bring a gate pulse that is also focused onto this crystal, as the terahertz wave propagates, it changes the birefringence of the crystal that gives rise to the polarization change of the gate pulse. As you do a scanning, you can map the terahertz electric field as a function of time, which can take up to several minutes to get a terahertz waveform like this. So my colleague and I developed a different technique to take advantage of the single shot readout from this by using this specially designed echelon mirror, which is basically a mirror with many stair-like steps. So once the gate pulse is reflected by the echelon, it splits into 500 delayed pulse separate both in time and in space. We focus these beams along with the terahertz pulse and then imaging this beam distribution in space. We can measure the terahertz signal in a single laser shot. So this is a terahertz signal that is averaged by 1,000 laser shot in just 1 second. And you can see that the correspondence between this new method and the conventional method is pretty good. And also the Fourier transform also show very good correspondence. So with this technique, we built a high-speed 2D terahertz spectrometer. The magic here is to use this echelon mirror and the high-speed camera so that we can measure the signal with very fast data acquisition time to really make our life easier. So we did this measurement first by driving either magnon mode alone. So if we drive these to FM mode and get this nonlinear frequency correlation map, we get all sorts of signals. But if you look at these signals, their detection frequency and the excitation frequency all correspond to the frequency of the harmonics of the frequency of this mode. And it's the same for driving the QAF mode. However, the surprise comes to us when we put the terahertz pulse at 45 degrees to start driving both magnon modes. And you can see the spectrum looks entirely different from the other two. And we get 4 immersion signals whose detection frequency, whose excitation frequency correspond to each magnon mode, but the detection frequency to the difference or the sum frequency generation, the 2 magnon modes.
Sorry, what was the difference between the second and third panels?
So for these 2 spectrum,
oh, you twisted some.
Yeah. So for this spectrum, we only drive 1 magnon mode.
Mm-hmm.
But for this spectrum, we drive 2 magnon modes and measure this nonlinear correlation signal.
Mm-hmm.
And what we found is that you can see these 4 peaks that do not exist in other spectrums and shows the correlation of different magnon modes. And then we can do a field dependence check. So we vary the terahertz magnetic field and measure how these signal strengths vary as a function of terahertz magnetic field. And they scales quadratically. So that means these signals step from second-order non-interactions, which originated from direct magnon-magnon mixing. And the reason why we see 4 peaks is because the sequence of excitation also matters. So we can either drive 1 mode first, followed by driving the other mode, or we can drive the other mode and followed by driving the first mode. So that gives you 4 peaks for both, for these signals, 2 for the sum frequency generation and 2 for the difference frequency generation. So this method not only tells us how these magnon modes are coupled, but also tells exactly the excitation pathway of generating these nonlinear signals. Yeah.
In the previous slide, do you have estimation of the magnetic field strength?
Yes, I think the magnetic field of the terahertz waveform is around 0.15 Tesla. Yeah.
For the maximum.
Yeah, for the maximum. It's not that high compared to the experiment the experiment by Professor Tobias Humphreys. But the trick is that we do this nonlinear signal extraction. So it's very sensitive to a nonlinear signal. Yeah. So this example of how we visualize the non-interactions between magnon modes. And really, it conveys the idea of 1 + 1 that is greater than 2, because when we drive 2 magnon modes, we can generate a signal that you do not expect in a linear response regime. Okay, so that concludes the first story. And the first story basically tells us that when we launch both magnon modes out of equilibrium, they can intermix with each other and generate a new signal. The next question is whether we can control the energy flow within the magnetic system by directing one magnon mode to the other magnon mode. So that's what I'm going to tell you about the Terahertz-driven magnon upconversion. So we focus on a very similar compound, in this case, erbium osulfide. We did a very simple experiment just by using a single cycle Terahertz pulse to drive the system and look at its response. But we put a well-grid polarizer to clean up the signal. So first, we just put a magnetic field aligned with the A-axis so that we expect to drive this low frequency QFM mode. And in time domain, we indeed see it. Now, if we rotate the Terahertz magnetic field by 90 degrees, so we should drive this QF mode, and we indeed see this fast oscillating QF mode in the time and in the Fourier space. Okay, now let's go to the non-intuitive channel, which is we detect a signal whose polarization is perpendicular to the instant Terahertz polarization. In this scenario, we drive one mode, but we try to detect the signal of the other mode to see if there is energy transfer between the two magnon modes. So first, we put the Terahertz magnetic field to be along the A-axis. So in a linear response regime, you should expect to drive this QFM mode. But in the detection, you can see these fast oscillating signals, which manifest as this QF mode. So that's really surprised us, because we drive the low frequency mode, but in this perpendicular channel, we see the high frequency mode that emerge. However, if we rotate the magnetic field by 90 degrees, so in this case, we drive the QAF mode in the linear response, but we don't see anything that appears in the perpendicular channel because there's no excitation of the QF mode. Okay.
Is that because you don't have the sensitivity to see it, or is it actually because it,
Yeah, I'll show that in the next slide, probably. That can answer the question. Okay, so that measurement is nice, but we cannot rule out any systematic error or something like that. So we can do a more systematic measurement as we did previously by using the polarimetry type of measurement to really map out the symmetry of the excitation. So in this parallel channel, we rotate the material and measure the QFM mode and QF mode respectively. And you can see that the QFM mode can only be driven when there is a magnetic component project onto the A-axis, and you need a magnetic field component project onto the C-axis to drive the QF mode. So that's expected in a linear response regime based on the magnon selection rules. Okay. Now let's go to this non-intuitive channel, which is the perpendicular channel. So in this case, if you follow the linear response, you should expect the signal to vanish every 90 degrees, because that means you drive one magnon mode, but detect the other magnon mode in a linear response. And you can see that that's indeed the case for detecting the QFM mode. So the signal always vanishes every 90 degrees. But for the QF mode, for detecting the QFM mode, you get these non-vanishing ends when you drive the QFM mode along the A-axis, but you can get some signal from the QF mode. So that indicates to us that we can achieve this magnon upconversion process, but we need to do some further checks. The first is that we perform this 2D Terahertz measurement so that we can get this frequency correlation map. You can see this bright single peak here in this particular channel, whose excitation frequency corresponds to the QFM mode, but the detection frequency corresponds to the QAF mode. So that means we activate upconversion channel mediated by driving the low frequency QFM mode. However, if we detect the same thing by driving the QAF mode, we don't see the counterpart cross peak here, which indicates that there is no down conversion process. So this upconversion process exists and is unidirectional. Then we can perform a field dependence measurement. And indeed, you see that it's not linear and it follows a quadratic dependence. So this process is second order in nature, mediated by this low frequency QFM mode. Okay, that is nice, but we also did something a little bit crazy. That is, we rotate the sample every 5 degrees, and we measure the 2D spectrum at each angle. So on the left, I'm showing you the 72 2D spectrum in the parallel channel. On the right, I'm showing you another 72 2D spectrum in the perpendicular channel. So in total, we measured 144 2D spectroscopy measurements, which was impossible before by using the conventional method. But with our technical development, we are now able to do this type of measurement within 1 day. So that's really something very exciting. And what you can do is that you can extract the cross-peak amplitude as plot them as a function of crystallographic angle. So in the parallel channel, you get these slightly distorted Clover patterns. And in the perpendicular channel, you get this two-fold symmetric pattern. If you remember the 1D polarimetry spectrum I showed you, this is isolation of the nonlinear signal with a non-vanishing end in the 1D polarimetry pattern. And if you just do a very simple LLG simulation, you can reproduce these patterns very well. Okay, so another thing we want to explore is that whether this process is universal in these canted antiferromagnets. Instead of just, trying with another compound, we basically did this temperature dependence because there is a spin reorientation transition that occurs between these two temperatures. As a consequence, the resistivity constant changes and the QFM mode also softens approaching this transition temperature. If you go below this temperature, there's also a change of the magnon selection rule because the magnetization is rotated by 90 degrees. Okay, so we did this measurement, this 2D measurement across a wide range of temperature. And what we found is that for all this measurement we did, we can see a bright cross peak, which connects the QFM mode and the QFM mode. That means the upconversion signal exists at all temperatures, even when the temperature is close to the transition temperature and you have a very large frequency mismatch between the two modes. Okay, so why is that? What's the mechanism of this magnon conversion process? So we did some LLG simulation and also look at the nonlinear equation of motions that governs the dynamics of two magnon modes. You can see that the linear response just basically tells you how the magnon modes respond to a weak Terahertz magnetic field. But if you extend the nonlinear equation of motion to the second order, these equation of motions are asymmetric for driving the two magnon modes. So for driving the high frequency magnon modes, there are two mechanisms that account for this magnon-mediated upconversion process. One is this magnon photon process, in which you first drive the low frequency magnon mode and followed by another terahertz photon with the frequency of the different frequency component so that you can upconvert the low frequency magnon mode to the high frequency. And the second process is more interesting. That is, when you drive the low frequency magnon mode to the second order, it can non-linearly couple to the high frequency magnon. Okay, so can we distinguish these two processes. We did this by plot the upconversion amplitude as a function of temperature in this plot. And you can see that this trend is very non-monotonic, and you get a peak around 200K. If you do a simulation, account for each process alone, for the magnon-photon upconversion process, you get this relatively broad and flat signal contribution. However, if you do the same thing for this magnon-magnon coupling process, you indeed get a peak at around 200K. And that's a temperature where the low frequency magnon peak match the half frequency of the high frequency magnon peak. So you get parametric condition that start to play a role. So in this case, that's where the magnon-magnon coupling can dominate the process. And if you take a combination of two processes, it really reproduce the experimental observation very well. So in this case, we discover a combination of two different excitation pathways, but both pathways are mediated by the driving of the low frequency magnon. Okay, so that basically concludes the previous two stories in which we discovered several different processes involving nonlinear interactions between the magnons. And by developing our understanding of this system, now we are at a stage that we can rationally design the pathways to achieve some functionalities that we want. So in the third part of the story, I want to tell you how we achieve stimulated parametric downconversion or parametric amplification of the magnon modes. So there is a very interesting work recently done by the Professor Kimmel's group, in which they did a similar 2D Terahertz measurement by driving the system with a pair of strong Terahertz pulses. So in this case, they put the Terahertz pulse at 45 degrees, but the first, so that the first pulse can initiate the response of a high frequency QFN mode. And then the second process provides a magnetic field component to give rise to this down conversion of the low frequency magnon mode.
This is the same.
Is another also ferrite, so it's another antiferromagnet which also holds the two fundamental magnon modes. So by doing so, they are able to achieve a down conversion of this low frequency magnon mode in a nonlinear case. Okay, so but our understanding is that when you tune the magnon frequency to the parametric amplification condition, we are able to take advantage of magnon-magnon coupling to enhance such nonlinear signal. So is that the case? We did the same type of measurement, a similar type of measurement, by putting the Terahertz pulse polarized at 45 degrees. So in this case, we put another wire grid polarizer to select the signal that is only sensitive to the low frequency QFN mode. So we drive both modes, but detect the signal that is uniquely sensitive to the low frequency mode. And then we can perform the same 2D type of measurement and get signal looks like this. So we indeed found that if you take a spectrum line cut here at room temperature, whose excitation frequency corresponds to the high frequency mode, you see there are two peaks, one with a frequency corresponds to the low frequency mode, and that's the same process discovered by the Kimmel group. And the other, you can see another peak whose frequency corresponds to the difference frequency of driving two magnon modes. So that's from the magnon-magnon coupling. Now we can change the temperature to below room temperature and then to 20 Kelvin, which correspond to the parametric amplification condition. And you can see that these two peaks emerge into a single peak, and its amplitude is much larger than the previous two. And if you go away from this parametric amplification condition to lower temperature, these two modes also get separated from each other. Okay, if we plot this spectrum line cut as a function of different temperature, we can visualize more closely how this spectrum evolve as a function of temperature. So for the different frequency excitations, for the different frequency excitations, I think it's this one. So they goes up, they become lower in frequency when we increase the temperature. And for the field-driven down conversion, when you increase the temperature, the frequency goes up. And at some point, at this 200 Kelvin, they meet with each other and give rise to a single peak whose amplitude is much larger than those at other temperatures. So if we plot this down conversion signal as a function of temperature, you can see this trend with a peak at around 200 Kelvin, and its amplitude is much larger than the combination of the two peaks at other temperatures. And this trend can be reproduced by solving the nonlinear equation of the spin motions by taking account this parametric amplification from the magnon-magnon coupling. So it is magnon-magnon coupling that gives rise to this enhancement at 200 Kelvin. So if you think about this, this is very intuitive to understand. So in this counted antiferromagnetic material, if there is no parametric amplification condition, when you drive the two modes, it gives rise to the difference frequency generation, as I showed you in the first story. But when you tune the magnon frequency to reach half of the high frequency magnon modes, this difference frequency generation also provides another force to further drive this low frequency magnon mode, which is basically what parametric amplification is. And this is a stimulated version of the spontaneous parametric amplification phenomena that people have known for many years in ferromagnetic case. Okay. If you are familiar with nonlinear optics, you can find the exact analog between this nonlinear optics and nonlinear magnonics. So when you shine a single frequency light to the second order nonlinear medium, you can generate two lights with a frequency at half frequency of the fundamental excitation to conserve energy and momentum. If you bring another light with a different frequency, you can generate a different frequency excitations by driving this second order medium with two laser pulses. Now, if you tune the frequency to get to these parametric amplification conditions, the different frequency also provides a stimulated force to amplify the seed signal of the second laser beam. And that's exactly the analog of this nonlinear magnonic process. Okay, I think we can get to the summary slides. So basically, I told you three tales of how nonlinear magnonics works and how they can play a role in driving and controlling the magnetic excitations. As an outlook, we can think broadly about other nonlinear electrodynamics that involves coupling between different modes in other quantum materials. For example, in Van der Waals magnets, you have this spin lattice coupling. So you can control the coupling between the spin and lattice degree of freedom. In charge density waves, you have this amplitude and phase mode, and you can think about nonlinear coupling between them. And in multiband superconductors, you get this Higgins and Lagrange mode, and you may also induce some dynamic coupling between these fundamental modes. So that's the direction that we are working with along this line. Okay, with that, I would like to thank my advisor, Professor Keith Nelson, and all the collaborators I had the privilege to work with, and also the funding from DOE. And I'd like to thank you for your attention. I'm happy to take questions.
Thank you, Zhuquan, for such a great talk. Let me open the floor for questions, both online and here.
I can just,
Do you have an estimation of the coupling strength between these two modes in terms of milli?
Yeah. So that's a good question, but it really depends on the temperature, or in other words, like the frequency matching between the magnon modes. We only see very strong coupling when we reach the condition where the low frequency magnon modes match the high frequency of the high frequency one. So in that case, you can get a strong coupling that dominates the nonlinear signal, but at other temperatures, the nonlinear signal is much weaker because you don't take advantage of this sort of coupling. And if I remember correctly, the nonlinear signal in the upconversion example is probably like below 10% compared to the linear signal. But with further technique development and laser development, you can visualize that when you really drive the system strongly, the nonlinear channel can overwhelm the linear channel.
I have a question on the materials.
Yeah.
What's the spin state of iron in this compound? So basically, what's the effective magnetic moment that you have in here?
It's basically in the new unit cell, the iron that provides
Is it 3/2? Is it 5/2? You know,
5/2. Yeah.
do you think that this is just because you're in a large spin limit that you can see these nonlinear effects? Like if I think about more quantum spin 1/2, you expect these effects to happen too?
So from our modeling, we believe that for canted antiferromagnet, this phenomenon can occur, but it's a matter of the strength, right?
Have you thought of like strontium iridate, for example, trying to do this? I know that Getty has been working on that compound.
Yeah. So we are pushing this direction to other materials like multiferroic, for example. So in that case, you can drive the magnon mode more strongly with the electric field.
Because you're probably again closer to the classical limit. I really would like to see a spin 1/2, which
Yeah.
if 1/2 is the that's my curiosity.
Yeah.
Any other questions online or in the room?
I have a very silly question that, just evidence is my better. Why you see only two sharp magnon modes? Why did you not see something more dispersive or broader?
So this is a class of material which are known to be this very good antiferromagnet. So you really get very sharp like magnon modes with very long coherence time.
Right, but I mean, the magnons are dispersive, right? So
yeah, but so here we use a Terahertz light to excite magnon modes around the zone center, and it's not that dispersive around. Yeah.
But
okay, if there are no other questions, yes, thank you. Keep having on.
where's the question?
Yes,
Everything.
Eugene, please, you'll mute yourself.
Hi, thanks for the great talk. I have two
1
questions.
second, we cannot hear you just yet.
Oh, you do not hear me? Okay. So, my first question is, are you expecting like HHE in the setup, like high harmonic generation?
Yeah, that's a good question. So we are still working along that line. So in principle, if you drive the system hard, you can get high harmonic generations from the magnon system. But so far, at least in this talk, what I talk about are only second order nonlinearities. So if you go to higher order, you can think about those terms, but they are much weaker than the low order nonlinear terms.
Okay, thank you. So my second question would be maybe a little bit irrelevant. So I'm working on a project on the HHE magnetophonics, and for that we require like a steady laser field, like a continuous laser field in the terahertz regime. So I was wondering, like being a theorist, I don't know much, I don't have much information about the experiment. So I was wondering, is there like a new way to use maybe this setup or like the terahertz pulse lasers as a continuous wave lasers? Like, is there any new setup to be able to use the pulse lasers are usually more sophisticated than the continuous wave. Is there any new ways to, use them as the continuous wave laser field?
So for the 2D test measurement that we are doing, we cannot use the continuous terahertz source. But the good thing about our measurement is that we can really see how energy transfer occurs within the magnetic system. So for example, if you can see this, when you see these second order signals, you know how they are driven and you can follow the excitation pathway. That's the uniqueness of our technique. I don't know if that answers your question.
Yeah, thank you so much.
Okay, if there are no other questions, let's thank you again for the time. This concludes the first previous seminar at Coherent.